Calorimetry is an experimental technique that involves the measurement of heat changes associated with physical or chemical processes. In laboratory, such changes are measured in a calorimeter. These measurements are generally carried out under two conditions: at constant volume, QV, and at constant pressure, QP. The experimental technique of calorimetry actually involves two steps. First step is the determination of heat capacity of a calorimeter. The second step involves the determination of the change in temperature during the completion of the reaction, assuming that it is an insulated system and no heat is exchanged with the surroundings. Let us first discuss the measurement of heat change at constant volume, or the internal energy change, delta U. The reactions that can be most easily studied under constant volume conditions are the combustion reactions, and the apparatus used for this purpose is called the bomb calorimeter. It consists of a sealed constant volume steel container known as the bomb, in which the reaction takes place. The bomb can withstand high pressures. A known mass W grams of a combustible substance is placed in the bomb, and oxygen under high pressure is introduced into the bomb. The sealed bomb is then immersed in a known amount of water contained in an insulated container. As the container is insulated, there is no heat exchange with the surroundings, and the reaction process is adiabatic. This whole setup is called the bomb calorimeter. The sample is ignited electrically, and the heat produced by the combustion reaction is absorbed by the water surrounding the bomb. The increase in temperature of water, delta T, is noted, and the heat produced is calculated using the equation QV is equal to CV multiplied by delta T, where CV is the heat capacity of the calorimeter. The measure of a bomb calorimeter's heat-absorbing property is called its heat capacity. Each bomb calorimeter differs from all others in its ability to absorb or release heat. The heat capacity of each bomb calorimeter is determined experimentally. Heat capacity of the calorimeter is determined separately by igniting a known amount of a substance, whose heat of combustion is already known, in the same calorimeter. And CV is equal to C multiplied by M, where C is the specific heat of water and is equal to 4.184 joules per Kelvin per gram, and M is the mass of water. Actually, heat capacity of the calorimeter or the system is the sum of heat capacity of the bath, that is, water, and the heat capacity of the bomb, that is, the metal. Water has high value of heat capacity as compared to the metal of the bomb. Thus, heat capacity of the metal is neglected, and the heat capacity of the calorimeter is taken as the heat capacity of only the bath. This QV expressed above is the heat evolved when combustion of W grams of the substance takes place. Since heat of combustion is defined as the combustion of 1 mole of a substance, therefore, the expression for molar heat of combustion becomes molar heat of combustion is equal to CV multiplied by delta T multiplied by M by W, where W is the mass of the substance taken and M is the molecular weight of that substance. As the above reaction is carried out in a closed vessel, therefore, heat evolved is the heat of combustion at constant volume and is a measure of internal energy change, delta U. Let us now measure the heat changes at constant pressure. To measure the heat changes at constant pressure, a device known as a coffee cup calorimeter is used. These calorimeters are open to the atmosphere, so these measure heat changes at constant pressure. This calorimeter is a foamed polystyrene cup partially filled with a known volume of water and fitted with a stirrer and a thermometer inserted through the lid of the cup. When a reaction occurs in the coffee cup calorimeter, the heat change is measured in terms of the change in the temperature of the system. Heat flow in the system is calculated by using the relation QP is equal to specific heat multiplied by M multiplied by delta T, where QP is the heat flow in the system, M is the mass of water in the coffee cup in grams, and delta T is the change in temperature. Specific heat of water is taken as 4.184 joules per Kelvin per gram. Therefore, the formula for calculating molar enthalpy delta H substance is delta H is equal to M multiplied by specific heat of water multiplied by delta T divided by N, where N is the number of moles of the reacting substance in the system. It is important to note that when heat is absorbed or evolved by the system at constant pressure, we are actually measuring changes in the enthalpy. Therefore, delta H is equal to QP. In an exothermic reaction, heat is evolved and the system loses heat to the surroundings. Therefore, QP as well as enthalpy change delta H is negative. Similarly, for an endothermic reaction, heat is absorbed by the system from the surroundings and therefore QP as well as the enthalpy change delta H will be positive. The enthalpy change that accompanies a reaction is called reaction enthalpy or enthalpy of reaction. The enthalpy change that accompanies a reaction is called reaction enthalpy or enthalpy of reaction. The enthalpy of a reaction is defined as the amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactants as expressed in the chemical equation have completely reacted. Enthalpy change of a reaction is denoted by delta RH. Enthalpy of a reaction is expressed as the summation of enthalpies of products minus the summation of enthalpies of reactants, where AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, the enthalpy changes for the reaction of 1 mole of methane with 2 moles of oxygen forming 1 mole of carbon dioxide and 2 moles of water may be represented as follows. The knowledge of reaction enthalpy helps us in maintaining the conditions required to carry out the industrial chemical reactions at constant temperature. It also helps in calculating the temperature dependence of equilibrium constant. The enthalpy of any reaction depends on the conditions under which it is carried out. Thus, it's difficult to compare the enthalpy reaction value for different reactions. To overcome this problem, the values of delta H for different reactions are expressed at their standard state conditions. The standard enthalpy of a reaction is the enthalpy change accompanying the reaction when all the reactants and products are taken in their standard states. A substance is said to be in a standard state when it is present in its most pure state under a pressure of 1 bar at a specified temperature. In other words, when the enthalpy of a reaction occurs at 1 bar pressure and specified temperature, it is called standard enthalpy. For example, the standard state of liquid ethanol is pure liquid ethanol at 298 Kelvin and 1 bar pressure, and the standard state of solid iron is pure iron at 500 Kelvin and 1 bar pressure. Let us now look at the enthalpy changes during phase transformations. We know that the intermolecular forces in the 3 states of matter are different. Therefore, the amount of energy required to convert matter from one state to another also differs. Standard enthalpy is represented as delta H naught, where the superscript naught indicates the standard state. The process by which matter is converted from one state into another is known as phase change or phase transition. The enthalpy or heat changes accompanying these phase changes are enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Let's look at each type in detail. Standard enthalpy of fusion is the enthalpy change accompanying the melting of 1 mole of a solid substance in standard state into its liquid state. It is also called as molar enthalpy of fusion and is represented as delta fusion H naught. For example, the amount of heat required to melt 1 mole of ice at 273 Kelvin is 6 kilojoules. Thus, we can say that the molar enthalpy of fusion of ice is plus 6 kilojoules per mole. As the melting of a solid is an endothermic process, all enthalpies of fusion are positive. We know that freezing is the reverse of fusion. Thus, the enthalpy of freezing, also known as enthalpy of solidification, is the same as enthalpy of fusion, except that it has the opposite sign, that is, a negative sign. Now let's look at the enthalpy of vaporization. The amount of heat required to convert 1 mole of a liquid into its vapor state at constant temperature and under standard pressure is called its standard enthalpy of vaporization or molar enthalpy of vaporization. For example, the amount of heat required to convert 1 mole of water into vapor at temperature 373 Kelvin is 40.79 kilojoules. Thus, the molar enthalpy of vaporization of water is plus 40.7 kilojoules per mole. We know that condensation is the opposite of vaporization. Thus, the enthalpy of condensation has the same value as the enthalpy of vaporization, except that it has the opposite sign, that is, the negative sign. Now, let's look at the enthalpy of sublimation. Sublimation is a process in which a solid changes directly into vapor state without any intermediate liquid state. Enthalpy of sublimation is defined as the enthalpy change accompanying the conversion of 1 mole of a solid directly into vapor phase at constant temperature and under standard pressure. For example, the amount of heat required to sublime 1 mole of iodine is 62.4 kilojoules. Thus, we can say that the molar enthalpy of sublimation of iodine is plus 62.4 kilojoule per mole. The magnitude of the enthalpy change in phase transformations depends on the strength of the intermolecular interactions between the molecules in the substance undergoing phase change. For example, it requires about 40.79 kilojoules of energy to vaporize 1 mole of water, while it requires only 29 kilojoules of energy to vaporize 1 mole of acetone. This can be explained in accordance to the fact that the water molecules are held together in the liquid state through hydrogen bonding, while the acetone molecules are held together only through weaker dipole-dipole interactions. Thus, it requires less heat to vaporize 1 mole of acetone than 1 mole of water.